Thank you, Tracy, for the kind introduction, and welcome everyone. I'm glad that you're here. I would like to talk today about decarbonization of islands, and especially putting a little focus on engines and turbines and the role that they can play on those islands. But before I start, let me introduce where I'm coming from. I'm working at MA in Energy Solutions, and our ambition there is to really move big things to zero. And what we mean by that is that we want to especially look into sectors that are hard to abate, so where it's rather difficult to reduce the CO2 emissions. And we have here some examples. I've brought 5 examples. So starting here with the heat pumps. So we also produce big heat pumps, and we just recently have commissioned a project in Denmark, where we substituted a coal power plant that was used to produce heat for the district heating, and this is now being supplied with a large heat pump. And we are active in the carbon capture sector. We mainly provide there the CO2 compressors, which are needed for the sequestration of carbon dioxide. Then we have our daughter company, HTEC. They are active in the PEM electrolysis field. They build electrolyzers. And we believe that hydrogen will actually play a key role, especially in those sectors that are very difficult to electrify. And we also build reactors, and then eventually the entire system to produce green e-fuels from the hydrogen. We are very much active in the engine field. We are working on green engines as well, so engines that can run on renewable fuels, hydrogen, for example, or methanol or others. And this both for the shipping industry, so for very large ships, any ocean-going vessels, but also for the power generation sector. And then finally, the retrofits. I think that's also a very important aspect, really, maybe forgotten from time to time. We build a lot of big equipment that lasts many decades, like many other companies do as well. So if you have something in operation already and you still want to keep it operational for maybe another 10 or 20 years, it can also make sense to think about decarbonization there. Now that's a whole list of technologies, and sometimes it's difficult to find the right one for your goals, and this is one of the main reasons why we found the energy consulting team a couple of years ago. Our aim here is to help our clients find the best solutions for their problems, and we really want to advise them and help them to make good decisions, for good investment decisions, and also analytic-based investment decisions. But enough about that. Let me start with my presentation. I've brought here two diagrams showing the energy mix. The top one here, the world electricity generation mix from 2 years back. You see there we have around 13%, 12% of energy coming from solar and wind, which is not a lot yet. But I think it's still fair to say that the energy transition is already happening. And I've brought a second example from Greek here. They have already achieved around 1/3 of energy or electricity coming from PV and wind, so they're already one step further. And yes, once you have reached a certain level, and I've heard this several times already here, it becomes harder and harder to further achieve decarbonization. And I really would like to focus today on sort of the next level of decarbonization. So what happens when you want to go 70 or 80 or 90% of decarbonization or CO2 neutral, or even maybe 100. And for that, I set up a generic study about an artificial island. So my guiding question today will be, how do you actually decarbonize an island grid, or maybe even other bigger grids? And I think the first part, that's a no-brainer really. You put solar and wind power into your grid. That's the cheapest way to start the decarbonization. Of course, it depends on where you're located and your natural resources, and that's clear. But there are unfortunately also some limitations. due to the fluctuating supply. And then the next step typically is you add energy storage to your system, so typically batteries, for example, on an island. And this can bring you to an additional step of your decarbonization, so you increase your share of PV and wind power, and it's really a great way to do this. And yeah, also economically it makes sense in many cases. But again, there are some limitations, especially when we think about longer term storage. So there will be a remaining gap, and that, I think, could best be covered with flexible thermal power plants. So they cover the gap. They should only run, of course, when not enough renewable power is available. And ideally, you can operate it then later on with renewable fuels. And I've put here two different technologies that I think are very promising. We have an engine and a turbine, both very flexible. They can ramp up quickly. So they're a good match for renewables, really. So my question then was here, well, what's the best technology mix? And especially, what will be the number of thermal power plants that you need in the future, and which type would you select? The model that I set up, it's a typical situation that you could have on a Greek island. We have here a load profile, 250 megawatts peak power demand. The peak power demand is here in summer when all the tourists are there. Then we have the natural resources I also took from the region, and to also put a bit of grid stability issues in there, I added a capacity margin to the model, and also some reserve requirements, some raise and regulation reserve, totaling to 50% of the load requirements. Then I put in here some key assumptions. So it's an LT model, so a greenfield LT model. We have 5 different technologies that can be built. We have PV and wind here with typical values. Some of the key values I put here. We have the batteries, 85% round trip efficiency, also I think very typical. And then we have the engine and turbine. They distinguish mostly from the efficiency, so the engines are a lot more efficient than a gas turbine is. But then on the other hand, they are also more expensive usually, so there is an offset. So maybe the question is really, does this additional cost is this additional cost justified by the higher efficiency? Then I I looked at 2 different scenarios. I called the first one here the LNG scenario, and the second one the e-fuel scenario. In the first one, the idea behind that was that the grid operator or the utility of this island, they set a target and they said, well, maybe we want to go to 70% of renewable electricity and keep the remaining 30 coming from a thermal generator based on LNG. Or maybe we want to go to 80 or 90%. I fixed the fuel price here to 10 euros per gigajoule, typical price of LNG, and then let Plexos calculate what's the best way to cover this. So I put a constraint to the model that we achieve, the desired share of renewable electricity, and let Plexos then build batteries, engine, and turbine as needed. So that's the first scenario. The e-fuel scenario would be sort of the next step. Maybe we want to start here, stick with LNG, but later on go to an e-fuel. That would then, of course, be more expensive. I checked here prices up to 50 euros per gigajoule, and again, let Plexos calculate the best technology mix, but here there is no restriction as to how much PV and wind should be built. So it could be anything, and I wanted to find out here which part will, in the end, still be coming from a thermal power plant, and how much will be coming from batteries, PV, and wind. So here are some results, starting with the LNG scenario. You see here a diagram with the electricity generation mix. Here I set it to 70%, so you can see PV and wind, they add up together to 70%. And we have actually the engine covering almost the entire remaining or residual load. And there are still turbines, they also provide a little bit of load, but they're mainly there as backup. We look at what's being built by the model. You see Well, solar and wind, they add up to about 500 megawatts, so about 2 times what the peak power demand is. We have quite a lot of turbines, maybe half of that as engines, and also some batteries there. If we look at the capacity factors, we have typical capacity factors for PV and wind, of course. And what's most striking there is that the engines really have quite high capacity factors, almost 50%. And this is also why they provide so much electricity. So even though we have a lot of turbines being built, they're hardly running. They don't provide a lot of electricity. And only for that part that is doing a lot of generation, it makes sense to install the engines and use the high efficiency. I have done this also not only for 70%, but for a whole range of renewable shares. And that's what I've plotted here. We have the capacity built over the entire range of the renewable shares. What I find most striking here is that PV and batteries, they are like ramping up a lot. So from here onwards, I would say anything that is generated by the PV plants cannot be used directly anymore, but is being stored in the battery. And that's why both of them ramp up sort of at the same level. The wind, for example, here, that's rather stable. So PV is cheaper than wind, at least in my case, and that's why we see results like this. Looking at the thermal power plants, the turbine here going down quite a lot, especially here when the batteries pick in. So to me, that said, well, the batteries sort of substitute the backup power of the turbines. We still have some engines, a little less than over here, but we still have some engines. And if you look at the capacity factors, we had around 50% at 70% renewable share. That drops quite a lot, but still at around 30%. So it still seems to be economically viable to install both engines and turbines, really. Now let me come to the e-fuel part. So if you decide you want to leave the LNG or really the fossil fuels, go to e-fuels, just to remind you here, I did not put any constraint regarding the renewable share, but instead I varied here the fuel price. So this is where we used to be with the LNG. Now I increased it to up to 50 euros per gigajoule. I wouldn't dare say how much the fuel prices will actually be in the future. That I don't know. I talked to different people and I got a range of fuel prices, so this is also what's being reflected here. You see again, PV is increased a lot when you add more, when the fuel prices are higher, PVs and batteries really. But then at a certain point, I would say maybe here 20 or maybe 30 euros per gigajoule, there are not many changes visible anymore. So once you've reached sort of this price level, it doesn't really matter. I mean, you would always build the same. Looking at the demand coverage, you see here PV and wind, they cover now around 90% of all the electricity demand, and the generators covering the remaining 10%. And here it's quite striking. We only have engines left, no more turbines, and that's even though they don't really run a lot anymore, but the fuel prices are quite high, so that's why it still makes sense from an economic perspective. And I would like now to look a bit deeper into this comparison of turbine and engine on the next slide. On this graph here, I plotted the levelized cost of electricity. And what you saw on the slide before is here the 100% baseline. So of course the LCE is not constant when you increase the fuel price. It goes up. But this technology mix is really my baseline that I wanted to compare to. Now if you look at the engine curve in blue, you see, well, if you do not give Plexus the option to build both engine and turbine anymore, but you restrict it only to the engine as an option, together with PV, wind, and batteries, then your overall system fuel prices, your overall system electricity prices, they will be a little bit higher, so around up to, let's say, 4% 10% or so higher than if you have both options. If you go to higher fuel prices, there's no more difference visible. If you take away the engine as a build option and only have the turbine left, then you see that the overall ACOE of the system will be quite a bit higher. So here at LNG prices, it would be around 5% or maybe 6%. Then if you go here to e-fuels, it will be maybe around 10, 15%, something in that range. So, coming to my summary, and coming back to my original question, how you decarbonize an island. Well, the first thing you do, you build PV, wind, and battery, and that will give you already good coverage of your power demand, but there will be a remaining part. This remaining power demand best covered by engines and turbines, and in the LNG case, the engines will then be there to actually do the generation, whereas the turbines are mainly there as a backup. And then if you should you go further to e-fuels that are more expensive than the LNG, this would mean that no more turbines are built, but independent really of the price of the e-fuel, you will always have sort of around 10% of the energy still being provided by a thermal power plant, which is here best covered by engines. And I think this is a great result in terms of what decision you want to make, because even though you may not know today what you want to do in 10 or 20 or 30 years, if you want to stick maybe to LNG as a fuel, or if you may want to go to a renewable fuel, there's still a good way to go, and you could still make good decisions today what you want to build, because it does not change so much over time. With that, I would like to close and hand back over to Tracy. If you have any more questions, I'm more than welcome, or you're more than welcome to ask me, and I'm happy to answer. Thank you.
Thank you. Thank you very much, Moritz. Very, very interesting. Any questions? I have one at the back.
Hello, it was a very nice presentation. My name is Srđan Bošković from Tetra Tech, and I would like to ask you, did you take into account reserve for frequency regulation in your calculations? And how did you take it into account if you did?
Yes, I put in two types of reserve, so regulation reserve and a race reserve, and total of 15% of the current load.
Okay, thank you.
More questions? Okay, well, I have a question, Moritz.
Go ahead.
The question is it's always quite controversial, sources of different costs, levelized costs, investment costs. Mm-hmm. What sort of sources did you use? Did you use a range of sources, or did you stick on some tried and tested data sources?
No, well, I mean, I put them here on my slides, the values that I actually picked.
Yeah.
And of course, it's, especially when you talk about an island, it's really difficult to say how much it will be, because the logistics can be much more complex than in other places. So yeah, you can argue, I think you could argue a lot about what prices you want to put there. I just put prices that I would say are a good rule of thumb if you want to start. So I didn't really, did a lot of price changes in there.
Okay. No, thank you. Thank you. Very, very interesting. Another question?
Hi there, Michael from Wärtsilä. So just maybe two questions. First, in terms of the modeling resolution, what resolution did you use? And then the second question is, did you look at different weather years as well when you did the optimization?
Could you please repeat? I can
Sure. Sure. So the first question is around the modeling resolution. Mm-hmm. And then the second, did you use 1 hour resolution, 5 minutes?
1 hour resolution.
1 hour resolution. And then the second question is, in terms of the testing of different weather years, did you optimize the model looking at the different weather years as well?
No, I just picked 1 year. I actually only modeled 1 year in here, and I just took a solar and wind profile from Greece. southern Greece, really, yeah. So I didn't put any variations in there. But I don't think it would really change the results in general a lot. I mean, this is of course not meant to give an advice to a very particular island or a very particular case. It's more like a general study to show where things could be going. If you now had a very, like one project or one island or one case study really, you would need to go into a bit more detail of all your inputs basically.
Anything else? That reminds me a little bit of the talk we had from ESB this morning, talking about an island, the isolated nature. It adds huge pressure onto your analysis. You can't just rely on interconnectors to sort you out.
True, yes. I mean, connections to other grids would, of course, make a big difference.
Yes. Islands, particularly the island of Ireland, has always been I always think of it as the canary in the coal mine, always hitting the issues first. Lovely. Okay, well, thank you. Thank you very much. Thank you, Moritz.